dl is the length of current element, theta is the angle made by the current element with the line joining the current element with the point where we find the magnetic field. R is the distance between the current element and the point. And in vector form, we write dB vector is equal to V0 by 4 pi I dl vector cross R vector by R cube. Then I told you what is the magnetic field due to a straight current carrying conductor. I said magnetic field due to straight current carrying conductor is mu0 I by 2 pi R. Then I said you magnetic field due to a circular current carrying conductor at its center is mu0 I by 2 R, and at its axial point, which is R distance away from it, if radius is A, is given by mu0 I A square by 2 into A square plus R square power 3 by 2. I said you in each case how to find direction of magnetic field. If it is a straight current carrying conductor, use your right hand thumb rule. If your thumb is pointing towards direction of current, then the 4 fingers will point direction of magnetic field, and vice versa. It means if your 4 fingers is pointing direction of current, then your thumb will point direction of magnetic field. Both are valid. If you have a circular current carrying conductor and a circular current carrying conductor is taking the current like this, then the magnetic field will be into the plane. If it is taking the current like this, then the magnetic field will be out of the plane. Okay. So you can understand that we can use our right hand thumb rule in both the ways. In 10th you studied only about one way. In 12th you understand that both ways we can use our right hand. If thumb is giving current, 4 fingers gives magnetic field. If 4 fingers gives magnetic field, 4 finger gives current, thumb gives magnetic field. Then I taught to you, if you have a complete circle, you have the central magnetic field as mu0 I by 2R. So if you have an arc of angle theta, theta radians, then the B value will become equal to mu0 I by 4 pi R into theta. Theta should be in radians. So if you have a 90 degree or 180 degree or say 30 degree or 60 degree or multiple arcs, how to solve that kind of question I taught in the class to you. I also told you how if you have multiple loops given, one loop like this, one loop like this, one loop like this, one loop like this, and they are asking you to find the magnetic field at certain point, how to solve this kind of questions I have taught to you in the class. If there are 2 loops and they are asking you to find the magnetic field somewhere in the center, here, anywhere you can find it. If your concept is clear, you can use the formula, either it will be mu0 I by 2R or it will be mu0 I A square by 2 into R square plus A square power 3 by 2. Then I told you about Ampere's circuital law, which says that closed integral of B dot dl is equal to mu0 times the current enclosed by Amperian loop. Amperian loop is an imaginary loop which is used to enclose the current carrying conductors. We have derived this also by taking a straight wire, drawing Amperian loop and just finding and getting the answer. By Ampere's circuital law, solenoid's magnetic field is also found. We have not derived it, not required for the school examination, but the value of magnetic field inside the solenoid is B is equal to mu0 Ni, where N is number of turns per unit length. If you have 2 solenoids of 100 turns and 200 turns, does not mean that 200 turns will have more magnetic field until you know the length. If it is 1 meter, yes, 200 turns will have more magnetic field. But if it is 1 meter, 2 meter, they both will have same magnetic field. So magnetic field is a function of number of turns per unit length, not number of turns. If same solenoid is bent into a form of a circular form, it becomes a toroid, and then the length becomes circumference 2 pi r. Then I taught to you what is the force on a moving charge kept in a magnetic field, and force came as QVB sin theta, where Q is the charge, V is its velocity, B is the magnetic field, theta is the angle made between velocity vector and magnetic field vector. If both electric field and magnetic field is acting on a charge, then the net force on the body is called as magnetic Lorentz force, and that net force on the charge is equal to QE plus QVB sin theta, which can be written as Q into E vector plus V vector plus B vector. Then I told you what is the behavior of a charged particle entering a magnetic field. If a charged particle tries to enter the magnetic field normally, it starts taking a circular path. If it enters normally, the circular path says that it is having a radius of mv by qb, where m is the mass of the charge, v is the velocity of the charge, q is the charge on the particular charge or the particle, and b is the magnetic field. Very clearly indicating that radius is proportional to mass, inversely proportional to charge. Time period is 2 pi m by qb and frequency is qb by 2 pi m. Frequency and time period are independent of velocity. I also told you, if a charge enters a magnetic field making a random angle theta, then the value of r becomes mv sin theta by qb, time period and frequency remains same, pitch becomes 2 pi mv cos theta by qb. And what is that? If a charge tries to enter angle theta, it starts taking a helical path. If it is taking a helical path, the distance between two circles is called as pitch. I have taught in the class to you. Then we learnt about what is the force on a current carrying conductor kept in a magnetic field, and after derivation we found the value is ILB sin theta. I told you what happens if there are two current carrying conductors taking the current in same direction. They will attract each other with a force per unit length of mu naught I1 I2 by 2 pi d, where d is the distance between them. I told you if they are carrying current in the opposite direction, they will repel each other, and the force of repulsion will be mu naught I1 I2 by 2 pi d. So, the force per unit length of attraction repulsion remains the same, only direction changes. If they are having same direction current, they will attract each other. If they are having opposite direction current, they will repel each other. From this concept only, we also define 1 ampere. If you have seen the past year paper book, one question has come in the board examination, define 1 ampere. And if it is define 1 ampere, don't define 1 coulomb of charge flowing through 1 second will give 1 ampere. No. 1 ampere of current is that current which, when allowed to move through two parallel current carrying conductors having unit current, unit separation and unit length, experiences a force of 2 into 10 to the power minus 7 Newton. That is the definition of 1 ampere current. I taught you in the previous class. Then I told you what is the torque on a current carrying loop kept in magnetic field. I could derive and explain to you, torque on a current carrying loop kept in a magnetic field is NIBA sin theta, where N is the number of turns, I is the current, B is the magnetic field, A is the area of loop, and theta is the angle made between magnetic field and area vector. Magnetic field and area vector. If you write NIA as M, M is called as magnetic moment, then tau becomes equal to MB sin theta, or tau vector is equal to M vector cross B vector. Here you can write theta is angle between magnetic moment and magnetic field. By the use of this property, we derived or we found a device called as moving coil galvanometer, which is an electrical device used to detect a very feeble current. If you want to find a small current, you can find it by using moving coil galvanometer. Not only you can check the presence of current, you can also find its value. So what we have in an MCG, we have a current carrying a loop you have, and that loop is kept inside the magnetic field. The problem is we want to maintain theta as 90 degree. Why? Then only you will have the maximum torque, because torque depends upon theta. To do that, we provide radial magnetic field. So in MCG, what do you provide? Radial magnetic field. Why you provide radial magnetic field? To make sure that theta always remains 90 degree. So deflecting torque becomes NIBA. Same way, when the needle gets deflected, you want some device to bring it back to the original position. For that, we keep a spring below. A spring below is kept so that if the current comes, needle gets deflected, that spring will bring back the needle in the original position. That spring is creating a restoring torque, and a restoring torque is proportional to angle of twist. How much twist? That much restoring force. Less twist, less force. More twist, more torque. So deflecting torque is NIBA, restoring torque is K times theta, where K is torsion constant, theta is angle of twist. Then when you equate both, that is deflecting torque and restoring torque, what do you get? You get the equilibrium condition, which is NIBA is equal to K theta. From here you can write what is K by NBA. What is that? K by NBA? K by NBA is called as I by theta. Current per unit angle of twist. What is that called as? Galvanometer constant. It has another name. It is also called as figure of merit. I told in the previous class to you. This question comes in the board exam also. Define figure of merit. Figure of merit, if they ask definition, figure of merit is defined as current per unit angle of twist. Its value is K by NBA. Also, from here I can write, in the previous class we have found this, theta will become equal to NBA I by K, isn't it? Theta is NBA into I by K. Am I right? Very clearly you can see from here. Theta is NBA into I divided by K. Up to here we have seen in the previous class. So we came to understanding that when we make a device where we provide radial magnetic field on a current carrying loop, and when the current flows through loop, torque is created, torque turns the needle, restoring torque is created by the spring, it will bring it back to the original position when the current is not there, and that's how my MCG works. And since the current is proportional to theta, I can even measure the current, because how much needle will turn is depending upon how much current is coming inside. If more turn, more current, less turn, less current, you can measure the current. That's why by this MCG we can also measure the amount of current coming inside. Okay. So up to here we have seen in the previous class. Today we are going to proceed from there, and today we are going to learn a very important topic. Give the heading as sensitivity of galvanometer. Sensitivity of galvanometer. So first understand the meaning of the word sensitivity. What is sensitivity? Any idea? Sensitivity means large deflection for a small current. Large deflection for a small current. We want our galvanometer to be sensitive only. Then only you can measure it, then only you can find it, isn't it? So if your galvanometer has a good sensitivity, then only it can check the presence of small current, right? Now please pay attention. There are two kinds of sensitivity. One is called as current sensitivity, and second is called as voltage sensitivity. Current sensitivity is given by the letter IS and it is given by the letter VS. Now what is current sensitivity and what is voltage sensitivity? And I will give time for writing. Please everybody listen, understand. I will give time for copying. Don't waste time in that now. Current sensitivity is defined as deflection per unit current. Same way, voltage sensitivity is defined as deflection per unit voltage. Now, if you put the value of theta here, theta value already we have NBA I by K. I gets cancelled. IS will become equal to what? NBA by K. Question comes from here every year. Theory question comes, MCQ question comes, A and R question comes from here. So understand this concept well. VS will become equal to what? NBA I by K, and V is IR. I gets cancelled, it will become NBA by K into R. R is resistance there. So we came to know what is voltage sensitivity. Voltage sensitivity is NBA by KR. What is current sensitivity? Current sensitivity is NBA by K. I said in the beginning now that you want your galvanometer to be sensitive. You want it to be more sensitive. If you want it to be more sensitive, what steps you will take? By seeing this equation, tell me what steps you will take to make your galvanometer more sensitive.
Sir, increase the magnetic field.
Increasing magnetic field, very good.
Reduce the resistance.
Reduce the resistance, very good.
Increase the area of the
Increase the area of the coil, very good. Increase number of turns, very good. Very good. Decreases spring constant, very good. Okay, I'll come one by one. You said increasing the number of turns. If you increase the number of turns, more wire is used. More wire means more resistance. Trying to increase N, R will also increase. R is increasing, Vs will decrease. No change in Vs because of N increasing. So, number of turns increasing is actually going to only help you in current sensitivity, not in voltage sensitivity. Ruled out. I am not saying it will not, I am saying not favorable for doing that. Second, you told increase magnetic field. I told you in MCG we are using some magnets, right, round magnets for providing radial magnetic field. I hope you understand that those magnets are permanent magnets, not artificial magnets. So, how can you control the magnetic field? What magnetic field you used, that only will remain. You can use a strong magnet, but then you cannot control it. So, if you have a working MCG and if I ask you increase the sensitivity, you cannot increase by increasing the magnetic field. Yes?
Sir, then we cannot use the electromagnetic.
How? Yeah, already you are finding the current presence only. For that, so you will power your voltmeter by some appliance. Are you getting a point? It is meaningless. Third, you told area increasing. Yes, it looks like yes, area increasing will make your galvanometer more sensitive. True. But how much area will increase? You will make the MCG the room size. You will, for doing experiment, you will bring by using JCB one MCG. No, right? There is a limitation in that. This much big, this much big, this much big, this much big, that's all. If you make this much big also, it will become bulky. For experiment, you cannot go and make 5 people to go, come today we have MCG experiment. Bring 4 laborers. So, we have a restriction for that. I hope you are getting my point. Ask Sharon.
Sir, then this concept is entirely theoretical.
I will tell now. No, it's practical, man.
Having these many restrictions also?
I will tell now. Wait. So, number of turns increasing is going to affect my resistance. Magnetic field increasing, okay, fine, use strong magnet, but again, we cannot go beyond a limit because it's permanent magnet. Area will make your galvanometer very bulky. What remains? K.
Spring with less kappa.
Yeah, spring with less kappa or torsion constant. Spring with less torsion constant. So, what we do, whenever we want to increase the sensitivity, the down spring is there, no? That alone we will change to a more or less torsion constant spring. And what we will use for that, you know, what is the wire having less torsion constant? Any idea? Phosphor bronze wire. There is something called as phosphor bronze wire. This wire has low torsion constant. Since it has low torsion constant, it helps in increasing this current and the voltage sensitivity of a moving coil galvanometer. Are you getting? I am not saying that increasing N, increasing B, increasing A will not improve sensitivity. It will improve, but it will have practical difficulties in that. Okay? So, what is the best solution is use a spring with very low torsion constant. Clear? Tell me.
Sir, you said that even the permanent magnet we can't change it. Sir.
Hmm.
If you say that if we have the strong magnetic field, we can do something. But if we have the more strong magnetic field, then we can't sense the small current passing through it.
Why?
Sir, it needs more current to deflect again.
Yeah. So, you
Then now our main motto is to find the small current passing. Then if B is large means you can't sense the small current.
why you are saying like that? You are confusing between magnetic field produced by magnet and magnetic field produced by the current carrying conductor. See, the better magnet used, it's good for you only. This B is magnetic field produced by the magnet. Are you getting a point? And this I is the current flowing in the wire because of collecting through outside circuit. Don't confuse in that. Okay? So, all of you please copy it fast. All of you copy what you want to copy. I will wait for 2 minutes before I go to the next topic. Make it fast. Small concept only. Make it fast. Let me know if you are done. Shall I proceed? Okay. Shall I? So now next topic, last topic of this chapter, give the heading as conversion of galvanometer. Conversion of galvanometer. We will learn how to convert into ammeter. We will also learn how to convert into voltmeter. Converting a galvanometer into ammeter and converting galvanometer into voltmeter. Okay, now pay attention. I will once again give time for copying. That time you can copy. Please don't write anything now. Understand the concept. Again, a very interesting topic. Concept only is important. The writing you can get notes later also. Please, please, please. First of all, I would like to ask you, what is an ammeter? Used to measure the current. Okay, okay. So, ammeter should have a very big resistance or very small resistance. Why small? Loudly.
So I shouldn't have low resistance because already galvanometers have low resistance to.
Don't talk anything about galvanometer. If you are having an ammeter, my question like this I will put. This question has come in board exam also, MCQ. Ideal ammeter should have dash resistance.
Zero resistance.
Correct, 0. So always remember this thing, that ideal ammeter should have how much resistance? I'll tell you why also. Sharan Ram, if you have problem in this. Ammeter is used to measure the current flowing. Only if it has 0 resistance, it will allow all the current to pass through it. So you will measure the exact value of current. If suppose in the path you have some resistance, less current will pass, the current will go in some other path. Are you getting a point? So if you are somehow reducing the resistance, you can measure the current accurately. Ulta in the case of voltmeter, infinite. So answer is, if a question is coming, ideal voltmeter should have how much resistance? What is the answer? Infinite. So ideal voltmeter should have infinite resistance. Infinite resistance. This question has come in the board exam also. Ideal ammeter should have how much resistance? Voltmeter, infinite, ammeter, 0. Now pay attention. I have a galvanometer which is having a resistance, let me call it as G itself. G is the resistance of galvanometer. Think and tell me how to reduce its resistance. Suppose for example it has a value of 1000 ohms. 1000 ohm resistor is there of galvanometer. I want to make it less than 1 ohm. How I will make it? By
Connecting a resistor in parallel, sir.
what kind of resistance?
Shunt resistor,
What is shunt?
which means it will take most of the current and will allow only the needed current, sir.
Simple word, if I add a low resistance in parallel, shunt is the correct word what he is using, but what is the meaning of the word shunt? Shunt is low resistance in parallel. See, I have taught this to you, and very common sense thing. If you have two resistors in parallel, net value will be less than the least value. You know this? 10 ohm, 1 ohm. Put in parallel, answer will be less than 1. 1 by 10 plus 1 by 1 is equal to 1 by R. Solve, less than 1. 1 lakh ohm, 1 ohm in parallel. Answer will be less than 1 ohm. Are you getting my point? Always remember, when two resistors are in parallel, the R equivalent is less than the least resistance. Are you getting? So whenever you want to reduce a resistance, add a very small resistance in parallel, it will reduce the resistance. So how do I convert a galvanometer into an ammeter? By adding a shunt resistance in parallel to the galvanometer. And what is shunt resistance? Shunt means it is a small resistance or a low resistance which is going to allow maximum current to pass through it. Now, suppose the current I was coming and in this Ig was going, how much will go here? I minus Ig. You know that in parallel connection, voltage remains same. If you see the bottom and the above arm, you will realize that bottom, what is the potential? Ig into G. Above, I minus Ig into S. Don't you think so? I into R, here also I into R. They must be equal because they are in parallel connection. So, from here you can find the value of shunt resistance. What will be shunt value? Shunt value will become equal to Ig by I minus Ig into G. So, by this formula, you can easily find what is the shunt that you want to add in a galvanometer to convert it into ammeter. So, Ig is the current flowing through galvanometer, also called as full scale deflection current. I is the current going to entering the whole circuit. Ig is the current passing through the galvanometer. I is the complete current entering. And G is the resistance of galvanometer. Don't think galvanometer constant. Capital G here is resistance offered by the galvanometer. Something you are asking, Sharon?
Sir, any other way apart from adding something?
Somehow you have to reduce it. Yeah, the easiest way to reduce the resistance is add in parallel. You are having some 1 lakh, 2 lakh, 10 lakh ohm also. You want to make it very low. What you will do? Add something in parallel which is having low value already.
Sir, I'm asking about whether we could do anything apart from adding any resistance.
To reduce the resistance. No, I don't think. You want to make it shorter. Because we know R depends upon length, which she was saying, I think you're trying to say out area of cross section. Those things are impractical again. Making very small length, it's impractical. Simple ways, put in parallel one resistance, which is having a very low value already. Yes, Yogit.
Doing this, most current will flow through the
Shunt. Yes.
So that what is our main motive?
Our objective was to measure the current by ammeter. Now overall, suppose G had 1 lakh ohm, I added a 0.1 ohm resistance in parallel. Overall device is having a lesser resistance now. How much? 1 by S plus 1 by G. So this device became less in resistance, so it can use to measure the current. Got my point? Same way, if you have a galvanometer, I'm writing it here by a different color pen. If you have a galvanometer and you want to convert this galvanometer into a voltmeter, what you will do?
Add shunt to the series.
Why shunt?
Resistance.
Shunt means low resistance, man. Don't say shunt. Add a high resistance in series. Common sense. So if I am going to add a high resistance in series, let me call it as R itself. Then this full arrangement is called as voltmeter, which will have very high value, isn't it? Because I want to have infinite resistance for ideal voltmeter. So this current which was coming inside I remains same. So I can write the potential drop V will become equal to I into G plus R, isn't it? Do you agree with me? G was there already, the resistance of the galvanometer. R I have added. So G plus R into I will give you V, and from here you can find what is the value of R required. So V by I will become equal to G plus R. So from here you get R is equal to V by I minus G. I hope it is visible to all the online people also. V by I minus G. V by I minus G. Revan sir, you can change the mode. Is there inside? Okay, I will change the mode. So I hope now it will be visible to everybody who is online, the whole board. So you can copy the notes from here. Conversion of galvanometer into ammeter and voltmeter. Please copy this. We will solve some numericals now based upon this. First you copy this, then we will solve some numericals based upon it. Make it fast. I hope everybody is able to listen to me. If you are listening me, take the question now. If you have copied it, please take the question now. Question goes like, an ammeter of resistance 0.8 ohms can measure current up to 1 ampere. Can measure current up to 1 ampere. I will repeat. An ammeter of resistance 0.8 ohm can measure current up to 1 ampere. What must be the shunt? What must be the shunt to make it measure current up to 5 ampere? To make it measure current up to 5 ampere. Make it fast. Zero point 0.2. Correct. Good. 0.2, if you got it, is the correct answer. Simple question, everything is given. If you solve properly, you will get the answer. Have you got 0.2, people who are in online?
Yes, sir.
Then it's fine. Anybody has doubt in this question? If you are clear, I will give the next question then. If you are clear, I will give the next question. Shall I? Okay, take the next question. If you have doubt, I will solve on the board. Next question is, I will solve on the board, Pratap. Okay, give me a second. Take another question meanwhile. Question is, a galvanometer, good question, board exam question. A galvanometer can be converted into a voltmeter. A galvanometer can be converted into a voltmeter of certain range. By connecting a resistance of 980 ohms, by connecting a resistance of 980 ohm in series with it, series with it. When the resistance is 470 ohm, when the resistance is 470 ohm connected in series, the range is halved. The range is halved. The range is halved. Find the resistance of galvanometer. Find the resistance of galvanometer. Solve both these questions. I will solve. Pratap, I will solve this question also. Both I will solve on the board now. All of you give a try to this question also. After a couple of minutes, I will solve both the questions on the board. Please try. Answer given here is no, not in thousands. Think and say. Tell you, man.
Is it 40?
40 is the answer. Good, Ivan. Got. Mistake is mistake. Answer is 40 ohms. Others are getting that? No? You are also getting?
Yes, sir.
Okay, I will solve both the questions now. Last 1 minute for you to try. Then I will solve both the questions now. Shall I solve it? First I will change the mode. Yeah,
Sir, got the answer, sir.
got the answer? Good. Pratap, got the answer for this question? No?
So the first one you got it, sir.
Oh,
The second one,
first one you got it. First one anybody else wants me to solve? First one anybody else wants me to solve? No? Then shall I go to second question directly? Shall I? Anyhow, I'll just give you a hint of both the questions. So we know the formula of shunt is Ig by I minus Ig into G. Whereas to convert into a voltmeter, what is the formula of resistance to be added? V by I into G. V by I minus G, yes, V by I minus G. So I have the formula of resistance to be added in the case of conversion of galvanometer into a voltmeter, and I have the formula for finding the shunt, which will convert my galvanometer into a ammeter. Now the first question that I gave was based upon this. Can you tell me what are the data given, Shweta? What are the things were given? Of G. G is 0.8 ohm, then? So Ig is given as 1 ampere. Okay. So they are asking, they want to make it measure up to 5 ampere. What is shunt required? Everything is given. The formula you have to use S. I think Pratap, you got the answer already. Ig is 1 by 5 minus 1 into 0.8. That's all. So 1 by 4 times 0.8, which will give me 0.2 ohms. So if I connect in this 0.8 ohms, 0.2 ohm in parallel, I am going to get a ammeter which can measure 5 ampere current. So from 1 ampere, I increased my efficiency of ammeter by up to 5 ampere I can measure. Are you getting my point? Same way, in this question, what they gave? Yogi, what they gave in this question? Second question.
Sir, they gave resistance
How much?
value as 980. In the first case, they gave 980, sir.
R1 is 980 ohms. Okay.
And in second case, it is 470.
R2 is given as 470.
Here, their range, what they're telling is V by I.
And for R1, it is some range.
Ah.
R2, the range is
Half. Okay. So if the range here is V, here it is V by 2. Isn't it? That's only given? Okay. Because why I am saying range as V and V by 2? Because range for voltmeter is how much it can measure it. What to be measured? Voltage only, no? So here if it can measure V, here it can measure only V by 2. So what remains same? Current remains same. So one thing I can do here for easy calculation, I can write V. V was equal to I into G plus R, isn't it? This is the formula. So in the first case, it will become V is equal to I into G. G is
We need to keep like this. At last, we'll get the.
no. One thing, what is the value of G? R2. What they're asking to find this question? Galvanometer, relation of galvanometer. Okay, R1 is, huh? Okay, G they are asking. Okay. So it will become G plus 980 in this case, isn't it? And here it will become V by 2 is equal to I into G plus 470, if I am right, isn't it? Now what you will do, you can divide both. If you divide both, V by 2, what? Then also you can do. If you multiply 2 here, it will become V is equal to 2 times of I into G plus 470. Yes, any way you can use, no problem in that. So now you can equate both. You will get 2I into G plus 470 is equal to I into G plus 980. So II gets cancelled, and 2G plus 940 is equal to G plus 980. When you solve this, G will become 980 minus 940, which will become 40 ohms. Good question. Got it? Simple only. So I gave you an idea about how the questions are coming from this topic, converting a galvanometer into ammeter or voltmeter. Is it clear to you? Sure. Some more questions will be given in the worksheet, but practice us to you from this chapter. And with this, we come to an end of this chapter. I hope you are clear in this. Any problem in this chapter up to now? If you have, please ask me and we can make it more clear. I said you 1, 2, 3 and 4 are the chapters where you have to worry about. Read very hard for another 1 week, 10 days and become super strong in 1, 2, 3, 4. Fifth chapter onwards, things will become simple if 1, 2, 3, 4 is strong for you. Otherwise, 5, 6, 7, 8, 9, 10 to 14 will become difficult for you. It is in your hand what you want to do. Shall I start the next chapter then? Give the heading as magnetism and matter. We are entering chapter number 5 and give the heading as magnetism and matter. Okay. This chapter has 2 parts. Small chapter, 2 parts only is there. In one part, see, in the 4th chapter, we studied about magnetism by current carrying conductor. I told this to you in the beginning of 4th chapter itself. In chapter 5, we are going to study about magnetism by naturally occurring magnets. If you have a magnet, what is its magnetism? What is the force on the different 2 magnets kept near to each other? Magnetic moment and many principles of that. So, this chapter, in the first part, we will learn about magnets and magnetic properties. In second part, we will learn about magnetic materials, which are of 3 different types: ferromagnetic, paramagnetic, diamagnetic. Dia, para, ferro. Some knowledge of dia, para, ferro you may have from chemistry also, which will become very strong now in physics. It is going to come in detail in physics. So, these 2 parts, having only half an hour remaining in the class today, I will prefer to take the second part now and then I will take the first part in the next class. And second part only questions are coming more in the exam also, which is type of magnetic material. So, give the heading first as magnetism and matter, chapter number 5, which is magnetism and matter, magnetism and matter, and give the subheading as types of magnetic substances, types of magnetic substances. So, as I said, there are 3 types: dia, para, ferro. Before I enter into talking about any of these materials, I will ask some questions to you. Answer wisely. Okay. So, this question is strictly valid for the people sitting offline in the classroom. Then I will ask questions to you also who are in the online. So, question to you people is, see around yourself and tell me which of the materials around you are magnetic in nature. Watch strap, okay. What else? Motor in the AC, okay. I am not asking where magnet is there, I am asking magnetic substances. Yeah, motor AC is correct, huh? Board, okay. This part, I think it is metal only, yes, yeah, okay, huh? Camera rod, okay. TV, okay, good, yes. Fan is there. These lights have metallic plates, yes. Mobile phones have more plastic only.
Sir, we have that magnet matching that.
Yeah, this phone has some metals also, yeah, okay then. Door hinge, curtain rods, good. Okay, enough. I'll ask people sitting in online, some people I'll ask, like I'll ask Anbarasi. Anbarasi, around you, what you feel is magnetic substance you have around you, wherever you are sitting?
Laptop battery.
Laptop battery, laptop itself has a lot of magnetic substance, yes, then? Nothing else?
That's it, sir.
Okay. Pratap, what about you? Something you find around you, magnetic in nature?
Sir, this pen cap,
Okay, pen cap.
and then the belt hook or something.
Okay,
A
hooks.
hanger.
Okay, hangers, hooks. Okay. Nitish Raghav, you have something around you which is magnetic. You are putting a headphone.
Yes, sir.
Huh.
My headphone
Yes, your headphone. What else?
and I have a knife here, sir.
Knife you are having. He's sitting with knife in the class. What man?
Sir, it is.
Okay, okay, kept in the table. Okay,
Yes, sir. For cutting cardboard.
cutting cardboard. Okay.
Yes.
I think in tension you are having a knife. From this I remember a small story. I had one, when I was doing my schooling, one person was there. He used to study in college. We have an option of writing 12th also in college, junior college they will say. So that guy, when he used to go for the examination, he will go with a knife. And what he will do, he will sit on the table, chair, and he'll put the knife on the table. And then he will start writing the examination. Really, I'm saying. So, for making people not to disturb him, cheating, whatever he wants to do, he will do. Knife is kept on the right side. Who will come to ask anything to him?
What if someone takes that knife?
He has a power of holding that. Somebody comes to take, he will take before them. Some kind of rowdy kind of guy, he was there. That I'm talking about that boy. Don't try all these things in your school examination. They will dismiss you also. Coming back to what we are speaking. So yes, Mr. Nitish Raghav had a knife around him. Something, Kirti, what about you? Something you have magnetic around you? Okay, charger. Fine. Ivan, anything you want to add around you magnetic?
Grill gate, sir.
Grill gate. Okay. Now, let me not ask further. Tell me where. Earth. Oh, great. Earth is magnetic. Yes. Okay. Yeah. Now, before you start saying some more examples, let me tell something to you. When I asked you what are some magnetic substance near you, your brain started thinking which materials I think will get attracted by magnets. Right? You start thinking that way. And you start naming those things as magnetic. What if I say you, I am itself magnetic? What if I say you are also magnetic? What if I say you this wooden board is magnetic? What if I say you the water in the bottle is magnetic? What if I say you the food that you are eating, Leah Varshni is eating some chapati, something hiding, that also is magnetic. So, all the organic things also are magnetic. Human beings are magnetic. Almost everything around us is magnetic. Aware about that? Not aware about that. Hereafter you will be aware about that. So, we are going to understand about three materials now, if time permits. One is called as diamagnetic materials. Second is paramagnetic materials. And third one is ferromagnetic materials. From this topic, the question will come from the electron theory, which I am 100% sure most schools will not teach properly, or most of you will not understand properly. You will mug up and go, chi less than 1, more than 1, equal to 1, attractive, repulsive, like that you will mug up and go. But the concept, because I struggled in my school time, even after I start teaching, I was struggling. So I have read so many books to understand the concept. It has quantum inside, it has, that much deep I will not go. But I have to make you understand what is the meaning of diamagnetic substance, para substance, and ferro. A lot of chemistry and physics involved in this. So first of all, understand that whatever you see around yourself is made up of some element, right? That's what matter is. Everything that you see mostly is carbon, mostly. Plastic chairs are carbon, wood is carbon, some steel things will have some carbon, isn't it? Fibers are there. We are carbon, food I told is carbon, isn't it? Some of the things are glass, which is silicon, and other metals are there around you. Mostly what you told is ferrous, iron, and iron is ferromagnetic in nature. You not thought about para or dia itself, Because as per you, they are not magnetic. As per you, magnet means something which is attracted by a magnet. First, come out of that thinking itself. I can show you water, right, which you can never think it is magnetic, being repelled by a magnet. Do you know this? If I am having water, today I can give you an experiment. If you have something in your home, small things, you can check magnet will get repelled by water. What experiment I will tell you? Take one, if you can, don't try and disturb your parents at home. In a vessel, put some water. Okay. Then you should have a thermocol. A thermocol in which you are keeping a small test tube you can keep, or you can keep a thin, some kind of lid where you can keep some water, but it should be thin lid. That's why I am telling test tube, a small test tube embedded inside the thermocol, and thermocol kept over the water. Why I am doing all these things? Because I want to study very minutely whether water is getting affected by magnets or not. Setup is very simple. In a vessel, water, on the water, a thermocol, in the thermocol, one test tube embedded, a thin test tube, small test tube having water inside. You may say that for a few seconds the thermocol will move here and there if there is some wind in the room, but if there is no wind, completely silent room, it will get static in some time, right? It will move here and there for a few seconds and it will become static. It became static now. Now you bring a magnet, bar magnet, and you make it go near to it. You know what will happen? It will repel. Bring it more near, it will never stay there. It will keep on moving back. So basically, water is being repelled by the magnet. Why? How? For understanding this, one thing I not thought, now I only am thinking while teaching, that you have to have a knowledge of Lenz's law for this. Lenz's law comes in chapter number 6, electromagnetic induction. Without understanding Lenz's law, it is very difficult for me to make you really understand what is diamagnetism. So what I will do, I will hold here and I will go to EMI chapter for small 10 minutes. Next chapter is EMI. In that I will take a small part and teach you, then I will come back to diamagnetism, because I don't want to simply say as per Lenz's law. I want to make you understand what is Lenz's law first. Okay? For understanding Lenz's law, you should understand what is the meaning of electromagnetic induction. You know what is electromagnetic induction? In 10th it was there, which was out of syllabus, but you should know a little bit about electromagnetic induction. Electromagnetic induction is a phenomena by which a current is induced whenever there is a change in magnetic field. See, when Ørsted found that current can produce magnetic field, it was a great discovery, because we can replace magnets with solenoids to control the magnetic field more. But when the whole world was busy with finding the applications of current carrying conductor having magnetic field, there was a person who had a different kind of thought process. He was thinking, in whole universe, nature is symmetric. If current can produce magnetic field, why can't magnetic field produce current? Very great thinking he was doing that time, because till then the whole world was depending only on DC, direct current, batteries. So current was not there in India that time. Asian countries will not have current. Only America got current, because there our famous Thomas Alva Edison was there, and Edison only discovered this DC. Batteries were discovered by many people, but he was the person who commercialized DC. Batteries, he made power plants by batteries. That is this much big size, room size, he made big batteries, right, by using electrodes, anode, cathode, electrolyte. And that battery was used to power the whole home itself. So in home you will have bulbs, you will have fan, whatever you have, everything was running on DC current, direct current. But the problem in direct current is, suppose I want to power these 2-3 buildings nearby, I should have the battery in the same place. So if I want to light the whole village, every home or every 2-3 homes should have one battery setup. Big tension. and we cannot have great power also, limited power. And the whole world, wherever current was there, they were depending only on DC. This Faraday person, he was thinking, how can I produce a current which will not be produced by the batteries and which can be transported to longer distances? That is the time when, by doing a series of experiments, he found the concept of electromagnetic induction. So, electromagnetic induction is found by whom? Faraday, Michael Faraday. What did he do? He found that magnetic field cannot produce current, but changing magnetic field can produce current. Are you getting my point? So, what did he say? Faraday gave two laws. I will not write that laws now. I will teach you when EMI chapter comes. Faraday's first law, Faraday's second law. Faraday's first law said that whenever there is a change in magnetic field or magnetic flux, there is an induced current, and this induced current lasts till there is a change in magnetic field. It means if magnetic field is changing, current will be there. If magnetic field stops changing, current will also stop. So, if you want to produce alternating current, magnetic flux should keep on changing. First law of Faraday. Second law of electromagnetic induction given by Faraday. Second law of electromagnetic induction says that magnitude of induced EMF is rate of change of magnetic flux, d phi by dt, and phi is equal to Ba cos theta. I will teach that when the chapter comes. But he told that induced EMF, how to find the value of it? It is rate of change of magnetic flux. But Faraday did not give the direction of induced EMF. He told that induced EMF is produced. Whenever you will change the magnetic field, some current will come. That current is called as alternating current. But which direction current will come? He not gave. Could not speak about that. Who gave that? Lenz gave that. This is only called as Lenz law. So, Lenz law, Lenz was a scientist who gave direction of induced EMF. What did he say? Very interesting thing he said. Listen to me very carefully. Lenz said that direction of induced EMF will be in such a way that, I will repeat my lines, direction of induced EMF will be in such a way that it opposes the cause of it. It opposes the cause of it. It means the one who is creating the induced EMF, that will only be opposed by this induced EMF. Your parents gave birth to you, now you are opposing them, kind of, something like that. Imagine, now you will remember. So, I will repeat my statement. Direction of induced EMF will be in such a way that it opposes the cause of it. For example, I will give example also. If I am having this magnetic field, what is this magnetic field? Into the plane magnetic field. I think everybody knows by now. And if I am having a coil here, circular coil, just a coil, no current carrying coil. If this magnetic field is increasing, very careful, now it will confuse you, be attentive. If this magnetic field is increasing, if you ask me how, sir, many ways are there. Suppose there is a wire like this. Right side magnetic field will increase or not? If I increase the current is increasing, magnetic field will also increase. Magnetic field is changing, there will be an induced EMF in the coil. What will be its direction? Its direction will be in such a way that it opposes the cause of it. What is the cause of induced EMF here? Increase into the plane magnetic field. It has to produce out of the plane magnetic field. For that, the current must be in the anti-clockwise direction. Understood? So, direction of the current in this loop, this current is induced current, will be anti-clockwise, because anti-clockwise direction current only will oppose the cause of it. causes increase in into the plane magnetic field. Direction of induced EMF will try to decrease the magnetic field. To decrease the magnetic field, it has to produce out of the plane magnetic field. To produce out of the plane magnetic field, the current must be anti-clockwise. If you not heard me for a single second also in last 2-3 minutes, nothing you understood. Okay. Ulta. If the same coil, now current is reducing, then what is the direction of induced EMF? It will be clockwise. You know why? Current reducing, magnetic field reducing. Once again magnetic field is changing, so induced current will come. Induced current direction will be in such a way that it should oppose the cause of it. What is the cause here? Decrease in magnetic field. What induced current will do? Increase it. To increase the into the plane magnetic field, the current must be clockwise. Very deep, very, very deep. But very simple, if you understood this. I'll ask another question, one more better interesting example. Time, I think I will not be able to enter that topic itself. So now what I'm having a magnet falling into a ring. No current, a ring, metallic ring, and a magnet falling into the ring. Will any current come on the loop coil or not? Yes or no? Will any current come? First tell me that. No. Why it will not come here? The moment it tries to enter the magnetic field, this coil, magnetic field will increase or not? When the magnet is away, no magnetic field. When it's trying to come near the coil, magnetic field is increasing, magnetic field is changing. If magnetic field will change, current is induced. And that induced current will try to oppose it. What is the cause here? Increase in magnetic field. What induced current will do? Try to reduce it. To reduce it, it will repel it. To repel it, this side has to become north pole. This thing also I will teach you. For producing north pole, the current should be anti-clockwise. And to make it south pole, the current should be clockwise. So here there will be a anti-clockwise current, which will make this loop as a north pole. It will repel it. Not that much repulsion that it will go back, but it will repel it. This question has come in NEET examination also. NEET exam, this question has come. Question was, what will be the acceleration of magnet when it is trying to go inside this coil? Equal to g, less than g, more than g, 0. I'll repeat the question. It will be less than g. Why less than g? Because opposing, it will reduce. So it will still go down, but not with g as a constant. G will become lesser than 9.8. And once again, if it passed down, it has reached here now. South was here, north was here. Now what is happening? Magnetic field is reducing. Listen, 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 listen. Magnetic field is reducing. Magnetic field is reducing. Induced current will try to increase it. To increase it, it must become north pole. North pole to attract it back. Once again, G will reduce only. So answer is once again north pole. But north pole from down. So it is anti-clockwise from down, which is clockwise from up. This is confusing, no? See, what is the direction of my movement? Anti-clockwise for you, but for me, that's how it works. So from top, if you see, if something is looking clockwise to you, see the bottom, it will look anti-clockwise to you. Reality. This is actually clockwise, right? Anti-clockwise. Same thing down, clockwise. That's how it behaves. So when it is trying to go inside the coil, it is anti-clockwise from top. When it is trying to go down, anti-clockwise from bottom. Are you getting my point? If you are seeing from here, if you are seeing from here, anti-clockwise. If you're, for this case, it is clockwise actually. From seeing from down, anti-clockwise. Okay, I don't want to confuse you more in this, but the concept of Lenz's law is clear to you? Bad thing is I taught you Lenz law, but I cannot teach you why I taught Lenz law. Tomorrow once again you will forget. When I will enter the main part, you will forget this. Okay, time is 8:52, 56 actually. I will not be able to go into diamagnetism, sorry. It is a big interesting topic. But Lenz law would have gone inside your head something, right? Lenz law says that direction of induced EMF will be in such a way that it opposes the cause of it. So first step is check whether magnetic field is changing. Like for example, if I give a question to you, there is a wire carrying current. There is a loop in front of it. Whether any induced current will come in this loop or not, yes or no? Why?
Because current is increasing.
Who told current is increasing? Did I say that? So, current is constant. I not said increasing, decreasing. Current constant, magnetic field is there, but constant. Magnetic field not changing, no induced current. But if I say you, this coil is moving towards right. Now what has happened to magnetic field? Increasing or decreasing for that coil? Decreasing, because we know that if you go far, magnetic field reduces. So if this coil is going towards right, magnetic field is decreasing. Magnetic field decreasing, induced current will be there. So step 1 is identify magnetic field is changing or not. Step 2, check whether it is increasing magnetic field, reducing magnetic field. Step 3, if it is increasing magnetic field, put direction of induced current to reduce it. Or if it is reducing magnetic field, put direction of induced current to increase it. In this case, if it is going down, since the current was upward direction, here the magnetic field will be into the plane. So into the plane magnetic field is reducing. If it goes right side, it will try to increase it. So current will become clockwise, because clockwise will produce into the plane magnetic field. If you see NCERT book, EMI chapter, you have NCERT book with you? If you open it fast, come to NCERT book, EMI chapter. No, both of you don't have the NCERT book? Very good. NCERT book, all of you those who are in online also, NCERT book, EMI chapter, one small thing, I will close in 2 minutes, sorry. Something interesting going on, I don't want to stop in the middle. Example 6.4 you see, NCERT example 6.4 if you have book in front of you. I can open here also. It will take time. Open, downloading. What I should type? NCERT Physics. What? Chapter 6 PDF. Poduma. Kirti audible? Yeah, sorry, my battery was out. So this coil, rectangular coil, trying to enter the magnetic field. So what magnetic field is increasing? Into the plane magnetic field is increasing. So the direction of induced current will try to reduce it. If it tries to reduce it, direction of current should be how? Very good. Clockwise will produce into the plane only, no man? Anti-clockwise. So how the direction will be? If I draw it here, it will be like this. Yes, this is the answer. C, D, A, B. This question has come in the board examination also. See this question. It is trying to go outside. Magnetic field reducing. Inducer will try to increase it. Which kind of increasing? Into the plane increasing. Clockwise. Answer is ACBA. This is going to go outside, same like that. So it will be what? Anti-clockwise. Two answers only possible, man. So clockwise, A, B, C, D, A. Got it? This topic is Lenz's law from 6th chapter EMI. Based upon this only, we have diamagnetism concept. Now, in my next class, whenever I come, I will take the topic. Okay? For you, I will share some materials for you to study for the examination. Okay? Bye-bye. Take care. Good night. Those who want to drop can drop from the meeting. Bye-bye. Take care. Sai Rakshana, if she is there, she should not drop. She already dropped. Sai Rakshana, I will wait. Yes, I am there only. I am nowhere going, Pratap.